All right, so today we're going to talk about exponential functions, and we're going to evaluate them, and then we're going to identify and graph them. So today we're going to be looking at examples 1, 2, and 3 from this lesson. Tomorrow we'll do examples 4 and 5. So, all right, and then actually on Wednesday Wednesday and Thursday I will not be here. Mrs. Wiskevich will be here. On Wednesday, I will have video of me for you to observe. And then on Thursday, you'll just have some more practice problems. So, all right, so this table and graph show an insect population that increases over time. Notice that in the table, they are multiplying by 3 each time. And so on Friday, we talked about geometric sequences. Well, a geometric sequence is basically just an exponential function. It either increases at an increasing rate, which would be exponential growth, which we'll talk about on Wednesday, or it decreases at a decreasing rate, which is exponential decay. So we can see here that over the time of these 3 days, that this insect population increased exponentially. And that's the problem with insects, isn't it? They increase really fast. And you can see what happens with the graph, that the graph goes up increasingly also. That you notice that the big thing is, how do I know it's increasing at an increasing rate? Is the gap, either the gap between numbers keeps getting bigger, or the gap between points on the graph keeps increasing. So I know that it's growing in that case. So a function rule that describes the pattern above is right here at f of x equals 2 raised to the power, or 2 times 3 raised to the power of x. Notice that 2 is the starting population, and 3 is the amount being multiplied each time. So it's what we call that constant ratio. We talked about that the other day. So here's what a general form for exponential functions are. Okay, we're looking at f of x equals a times b raised to the power of x, where a is your starting value, okay, the initial amount you have, where you're going to begin, the value on the y-axis, okay, and b is the rate of increase or decrease depending on whether it's going up or down. Okay. So a is our starting amount, and b is how much it's going to change as a multiplier. And we'll refer to that once again as a constant ratio is what b is. We'll look at it as a value of r later on, but as a function, we have f of x equals a times b raised to the power of x. So here we have this function, 500 times 1.035 raised to the power of x, models the amount of money in a certificate of deposit after X years. And you know what? Good luck getting that rate nowadays. Okay? Anybody know what percent this represents? Good try. Okay? No, you were better the first time, Matt. Stop there, okay? All right. Ruth, is that what you were going to say, what he said, 103.5? Okay, it does, but really it represents a 3.5% increase, okay? Because we started at 100, okay, what you have now. But, I mean, so you're right. This number here represents 103.5%, okay? But when we talk about the amount of increase, we would say it's a 3.5% increase. Because if we said 100%, we just stay at $500 then, right? Well, that would never change because that's 1. So we've got the additional 3.5%. So it says, how much money will there be in 6 years? All right. So what do I do to find out how much money there's going to be in 6 years? Put a 6 where the x is. Very good. Okay. So we'll rewrite it. Oops, that won't bring it. As And we're going to, so what we're doing is we're finding f of 6 because we're replacing the x with a 6. So we get 500 times 1.035 raised to the power of 6. And so that's something then that you can just type right into your calculator. So 500 times 1.035 to the power of 6. 6. Enter. Right? So after 6 years, this person will have $614.63. So make sure you put your dollar sign on that number and have some kind of explanation of it. Okay. Like I said, nowadays those CDs are about 1.25%, where this one was 3.5. Your money won't increase that fast, unfortunately. Okay. Letter B. The function f of x equals 200,000 times 0.98 raised to the power of x, where x is the time in years, miles the population of a city. What will the population be in 7 years? Okay. So does anybody know what the difference is? If this says 0.98, what does that mean? Ruth, you know? Okay. Yep. We're going to have less than 200,000 people. All right, good. So we've got f of 7 then, because we're going to replace the x with a 7, equals 200,000 times 0.98 raised to the power of 7. Anybody know what the percent change is? Mitch, do you know what the percent change is? How shy of 100 is 98? 2. It's a 2% decrease then in the population every year. So what kind of cool number do we get? Okay. 173,625 point, we're always going to go 2 decimal places. 1 people. You can't have part of a person, but we're always going to take all of our numbers to 2 decimal places unless it asks us otherwise. Okay? Right? So you might say then that there's approximately, right? Approximately 173,625 people. Right? I still like to have a decimal number though. Okay? I prefer it. Okay? Do you get part of a person? Well, of course you're not going to get part of a person. But the point is that we're talking about an estimate. So here's the thing though. If I want to calculate more, which number is more accurate? The one with the decimal or the one that gives me the whole number? Okay. Right? The one with the decimal, okay, because it's a different number. So, okay. All right. So you calculate this one. Okay, remember that linear functions have a constant first differences, and quadratic functions have constant second differences. You guys remember calculating those to determine whether, okay, this is a linear, this is a quadratic. Okay. Well, exponential functions don't have constant differences, and here's that terminology I was using. They have constant ratios, which means that when we divide, we get the same amount each time. Right? And we did that on Friday. As the x values increase by a constant amount, the y values are multiplied by a constant amount. So it must be true that, first of all, when you're looking at these, First of all, the x values must increase by a constant amount. And then therefore, if the y values are multiplied by a constant amount, then we have an exponential function. And that function can be written in the form of f of x equals a times b raised to the power of x. So we're going to look at this next example then. We're going to look at a table of values, and we're going to determine whether that table of values represents an exponential function or not. So the first thing we do is we always look at the x's. All right, let me give you a chance to write this down. So if they give us a set of ordered pairs like they do here in letters A and B, we want to write them in a little table. You can, you don't have to, but a table will help you to be able to do the work you need to do. For most of them, most of you are going to figure it out right away. Some of you will have to do a little bit more work. So we want to tell whether each set of pair satisfies an exponential function. So we're going to look at the x values first. Are the x values changing at a constant rate? So for letter A, they go up by 1 each time. So if we calculated the constant differences, or first differences, we have 3 minus 2 is 1, 2 minus 1 is 1, and 1 minus 0 is 1. So then we need to look at the y values and calculate the ratios. So we're going to divide. Remember, when we divide, we do the next number divided by the previous number. So that's why it's important that you put these in order. So what's 12 divided by 4? 3. And 36 divided by 12? And 108 divided by 36? 3. Okay? So since all of these values here, are the same, then it is an exponential function. So yes, exponential function. And this would tell us then that if we wanted to write an equation for this, our starting value is 4, and our constant rate of change, or, well, multiplier, constant ratio, is 3. So we could say that this is a function that would be 4 times 3 to the power of x. 4 is our starting value, and 3 is how much we multiply by each time. Now, that's not something you need for this problem. For this problem, all we need is this, but that's just something to help you in the near future. So if I write it like this, I could do what with it then, if I wanted more numbers? What could I do with this if I wanted more numbers than just these 4 I have here? Okay, we could do that, right? Or we could just keep multiplying by 3, right? But if I had the function here, I could put it in my calculator and graph it then. Okay? Or look at the table. All right, letter B. Do these change at a constant rate? The x values. Okay, the x's all go up by 1 each time again. 2 minus 1 is, well, we're checking to see if they are exponential or not. So they may not be. That might be the problem with it. Okay? So could be the x's. Right? So those all change by 1, so that means that we can check the constant ratios then. So we get 0 divided by negative 64. What's that equal to? 0. Okay. Then we have 64 divided by 0. What's that equal to? That is undefined, exactly. Okay, good job. And so if the first one is 0 and the second one is undefined, can it be an exponential function? All right. So this is no, it's not exponential. All right. So check these two. Do both of these. Are they exponential? Does that set of data represent an exponential function or not? Okay, so we're going to do one more example. We're going to look at graphing. Okay? To graph an exponential function, choose several values of x, positive, negative, and 0, and generate ordered pairs. Plot the points and connect them with a smooth curve. All right? So this is why you have graph paper. All right? Take your calculator, set it down, turn it off, don't use it, because I'm going to expect that you're able to do these without it. Because hopefully every one of you could take this 0.5 times 2 to the power x, plug it in there and get a graph, right? Okay, you should be able to. Right? If you can't, ask me later, I'll show you how. But we need to be able to do these without one. And I'm going to show you, if you follow closely, I will show you how to kind of cheat your way through it. Okay? All right? In other words, there's a simpler way. Because sometimes you end up with small numbers that really don't work very well, or they're very hard to find. But if you do it in a certain manner, you can do it pretty easily. Okay? All right, so they want us to graph 0.5 times 2 raised to the power of x. So first thing we're going to do is we're going to make a table. And we're going to choose a couple of positive values, a couple of negative values. All right, so first we're going to go with negative 2 here. Oops, come on. Negative 2. And then negative 1. And then 0. And then 1. And 2. And actually what we should do is you should put another one down here, so let's add 3 to this. 3. We'll do one more. Okay? All right. Now, the easiest one of these, is always 0. Okay? Because what are we doing here? We are doing, this is 0.5 times 2 raised to the power of 0. Anybody know what 2 raised to the power of 0 is? 1. Okay? Anytime you raise something to the power of 0, it's 1. Okay? So if I take 0.5 times 1, what do I get? We get 0.5. Okay? Now, here's where our little bit of cheating comes in. Okay? Now, what does this number here mean? What's this number 2 mean in our formula? Okay? Remember, okay? This is A, that's B. Okay? A is our starting value, and B is how much it changes by each time, right? Okay? So if I had 0.5 here at 0, then to get the next number, I'm going to multiply by 2. So what's 0.5 times 2? That would be 1. Okay. And what's 1 times 2? 2. Okay. All right. So let's go up here then. Okay. So what happens if I'm going the other way, if I'm going backwards? Instead of multiplying 2 by 2, I'm going to divide by 2. Okay. So what's half of 0.5? 0.25. So this is 0.25. I don't know why it's putting them so big, but whatever. Just as long as it cooperates with me when I get done, I'm all good. And what's half of 0.25? Why not fix that? Well, what's half of 25? 12.5, right? So half of 0.25 would be 0.125. Man, let's hope this works for me. If it doesn't, I'm going to be a little frustrated, but I'll get over it. Okay? So, we're going to plot those points. And when we plot those points, if we've done our job right, then we will get something that looks like this. Okay? Now, don't you wish your paper would do that? All right, so let's talk about it. All right? So on your graph paper then, we need to make an appropriate scale. So you can go by ones, you can go by twos. I would go by ones. Okay? So we'll go by ones horizontally and go by ones vertically. And I'm going to undo what I just did so that we can do this together. Okay? So I might have, my graph might look like this. Right? So let's hold on before I get here a little farther. But this, I had that 3 down here that it doesn't like. Oops, no. There we go. There's 3. Okay. So we keep doubling, right? So if I double 2, I get 4, correct? So I'm going to have 4 down. All right, so let's plot some points so we can draw our line. Right. So I would use graph paper for this just because it's so much easier than doing it on line paper and because your graphs are going to be accurate, where if you use line paper, sometimes my in-between numbers don't work so well. Right? So we have the point 0.5. I'm always going to work with that one first. Okay? Start in the middle. And then 1, 1, and 2, 2, and we have 3, 4. Okay? Now, here's the thing to make sure of, is that one of the things I told you was that if you had the point 0, 0, it wouldn't work, right? Okay? If y is ever 0, it doesn't work. Okay? So when we draw our graph then, because now it's going to be kind of hard to put negative 0.25, right? It won't even let me do it because it's too precise. So if I take my pen or my pencil and I put, okay, there's negative 1.25. Here's negative 2 and half of that. Well, I'm getting really close to the x-axis, aren't I? Okay. So when you draw your line, make sure that you do not go below the x-axis. Okay? Make sure you're not coming up, but just make sure that it's coming along the x-axis here so it stays towards the bottom. But do not cross the x-axis because y cannot be equal to 0. Okay? They're always positive numbers in this specific case. And so that would be our graph there. So let's look at another one here. We want to graph y equals 2 to the x. What's the difference between this one and the one we just did? The other one had 0.5 in front of it, right? Well, this one has a 1 in front of it then, doesn't it? So this is like y equals 1 times 2 to the power of x. Like me. Okay. So this graph is going to look similar to that one, right? So we make a table, put negative 2, negative 2, negative 1, 0, 1, 2, maybe 3. When I put 0 in for x, what do I get? 1. 1 times 1 raised, or 2 raised to the power of 0 is equal to 1. Because it's 1 times 1. So when I double 1, I get 2. Double 2, I get 4. Double 4, I get 8. And then I go backwards. Okay. Now, if I just understood my handwriting here, so I could just flip that over there onto the graph, I'd be all set. The smart notebook's only so smart. Okay. So then we would plot those points. Oops. And then draw a smooth line. And make sure that we don't cross the x-axis. All right? Okay. All good? Easy stuff? Okay, so when you're doing graphs like these, make sure you put them on graph paper. Don't put them on notebook paper. Okay? I'm giving you graph paper. Use it. Put the graphs on graph paper. All right, so write your assignment down, then make sure your calculator, and if you borrowed a ruler, that your ruler gets back.